In this video, we're going to talk about mathematical modeling and variation. The first type of variation that we're going to talk about is called direct variation. And basically, direct variation is a linear model that has 0 as its y-intercept. In other words, the model will always look something like this. Y equals kx, where k is kind of like the m, right, for slope. So notice that there is no b because the b is going to be 0. So if you have a model that happens to have direct variation, it will always be set up in this way. Okay, so we'll have some kind of slope and 0 as the y-intercept. So there's a couple different ways you can actually say this. We can either say that y varies directly with x, or that y is directly proportional to x. Both of those things represent a direct variation, where again, the function is a linear function. It has a slope but no y-intercept. So you will see either one of these two ways as the way to be, or as the way to explain a direct variation type of problem. And k actually has a special name. It's called the constant of variation or proportionality. So if you happen to see one of those two phrases, it's talking about k. So we're going to take a look at an example out of your textbook, which says information about income tax being directly proportional to your gross income, which is actually true. So here's a couple pieces of information that they give us. So here's the information that it gives us. It says that we happen to have a state income tax of $46.05 for a gross monthly income of $1,500. In other words, if you get a paycheck for $1,500, the state's going to take $46.05 for your income tax. So the question is if this particular function varies directly, okay, or is directly proportional to x, then how do we actually make a function with this? So we have to actually determine which of these two values is my x and which one is the y. In other words, which one is independent and which one is dependent? Well, I know that for a fact that this number right here, at least for the time being, is going to stay the same. This is not going to change month to month if it's especially salary-based pay. So this is going to be my x. And this number can vary because income tax does change. So this is going to be my y. So what we're going to do to set this up is we're going to say, first of all, that my function should look like y equals kx. Since I have an x and a y, I'm going to plug them into my function. So this is going to look like 46.05 equals k times 1,500, or 1,500k. So the question is can we solve for the constant of variation? And the answer, of course, is yes. We're going to divide both sides by 1,500. Those will cancel. And I am left with k being equal to 0.0307. Now, remember that income tax is typically a percentage. So what would this value be in a percentage type of situation? Well, we move the decimal place over 2 times to the right, and it's going to be a 3.07% interest rate for your state income tax. So the function altogether is going to be this guy right down here in the bottom left-hand corner. So we have y equals 0.0307x. In other words, my rate of change in this particular function, or my slope, is that value. It's the percentage of your income. So as your income increases, your sales tax, or your sales income tax, state income tax, will be a multiplier of that particular decimal. So that's all direct variation is. So there's one other type of direct variation that we need to talk about, and that is direct variation is an nth power. Well, what does that mean? So we need to go into this a little bit and view an example so that we know what to do. In other words, this particular kind of direct variation relates one variable to a power of another variable. And a good example of this is the area for a circle, a equals pi r squared. So the way that we actually say this verbally for our area formula is the area A is directly proportional to the square of the radius r. And notice that there's no k in this particular function, so pi is going to be our constant of variation. Pi is definitely a constant in this particular case. Pi is a set number already. It is a constant value. So that's going to be our constant of variation in this case. So a couple different ways of saying this is A varies directly as the second power of r, or A is directly proportional to the second power of r. So in general, as long as we have this particular format, y equals kx to the nth power, this area formula meets that same exact criteria. We have an x and a y, they're just r and a in this case. Instead of k, we have a pi, and we do have an exponent on our independent variable. So as long as we have this form, it is still direct variation as an nth power. So we're going to take a look at an example. And this example says the distance a ball rolls down an inclined plane is directly proportional to the square of the time it rolls. And then it tells us that during the first second, the ball rolls 8 feet. And the first thing it wants us to do is to write an equation for this. And I know that it has to have this particular form. So we're going to change some variables if we need to, and then get our exponent in there. So our first variable is going to be distance. And our second variable is always going to be time. And notice too that it says that the distance is directly proportional to the square of the time. So time has to be our independent variable, and typically it always is. Our exponent is going to be a 2 because we're talking about the square of time. So we're going to get t for time and d for distance. And now to get our k, we have to be able to have some kind of coordinate. And we actually do. It tells us that in the first second, in other words, when t is equal to 1, my distance is 8 feet. So I actually do have a coordinate here, and I'm going to go ahead and do some substitution. I am going to take this information and just start over here instead so that I've got some more working room. But this is going to be 8 equals k times 1 squared. So we need to evaluate this real quick. This is going to become 8 equals k because 1 squared is just 1 and 1 times k is k. So we actually have just solved for k. That's awesome. So our final direct proportional equation is going to be d equals 8t squared. So this is what I'm going to work with. So we can actually ask ourselves a follow-up question for this. How far will this ball roll after 3 seconds? Well, now that we have a function to work with, all we need to do is plug stuff into it. So I'm going to say d equals, since that's what I'm looking for, 8 times 3 squared. So we square, oops, I'm sorry. Yeah, no, that's right. I'm sorry, I thought I made a mistake there. So 3 squared is 9, and we have d equals 8 times 9. And 8 times 9 is 72. So our ball will roll 72 feet after 3 seconds. So the next kind of variation that we have is something called inverse variation. And in this particular case, our general formula is y equals k over x. So instead of them being multiplied, they're being divided. That's why it's called inverse. And the way that you can say this is that y varies inversely with x, or that y is inversely proportional to x. And just like direct variation, we can actually see this as a power as well. In other words, that y is inversely proportional to the nth power of x. So this is just some of our basic information for inverse variation. So just as a really quick example, let's say that we have this coordinate. So we're going to have 0 represent time, so our initial time, and we're going to then have 15 represent our distance, and we're going to do this in feet just like the previous problem. So let's say that this particular situation is inversely proportional. We would get our general form set up, which is y equals k over x. And you have to know in the context of the problem if it's just that y varies inversely with x or that y varies inversely with the nth power of x. In this particular case, we're going to use y equals k over x, but just be careful about the context of your problems because this general form may have to have an exponent on the x instead. So let's go ahead and continue this. So I'm going to go ahead and plug in my t and my d into my general formula. So d is equal to k over t. We're then going to plug in our two values. So 15 is equal to k over 0. And if we see where we are right now, this is actually creating a problem. I have k being divided by 0, and that can't ever work. So this is something to keep in mind as you go through inverse variation. You got to be careful if you got a 0 in the denominator. We're going to actually go ahead and change this real quick. We're going to make t equal to 1 instead, just like so. So we're going to go through the process. K divided by 1 is simply k. So my k value here is going to be 15. So my overall equation for my final answer is going to be d equals 15 over t. And that's all there is to that. So there's only one more kind that we need to look at, and it is called joint variation. And the reason why it's called joint variation is because it contains both direct and inverse variation. So this is its general form. Z equals k, which is our constant of variation, times x and y. So instead of just having two variables, this is a particular case where we actually have three. And of course, another variation of this is that I could have powers on my x and powers on my y. So again, you just have to be careful about reading the context of your problem in order to figure out which general form that you need to use. And we just say this basically the same way as the others. We would say that z varies jointly as x and y, or z is jointly proportional to x and y. One of those two ways of seeing that will tell you that you're working with joint variation. So here's our example. We're going to have the simple interest for a certain savings account is jointly proportional to the time and the principal. After 1 quarter, which is equivalent to 3 months, the interest on a principal of $5,000 is $43.75. So let's first go through this and make sure that we can identify our three variables, because that's what joint variation has. So I see the word interest, and that is in fact one of our variables. So we're going to have interest be our capital I. We also have principal, which is going to be capital P. And we're going to have our time, we're talking 1 quarter or 3 months, be T. And we are going to have T be in years, because that's typically what is important when we're talking about a simple interest for any kind of account. So what we're going to do is figure out what's going to be multiplied together. In other words, up here, what's x and y, what is z? Notice also in this problem that it tells you nothing about being equivalent to the square of time or the cube of the principal. So this form right here is out of the question. We don't even have to use it. So we are going to be using that first form. So if we look at our question carefully, it says that interest is jointly proportional to the time and the principal. Those are the two variables that are representing x and y in my general form. So I is going to represent z. Time and principal are going to be my x and y. So here's going to be my new formula. So interest is equal to k, our constant of variation, times the principal times time. So we need 3 pieces of information to plug into this formula so that I can actually solve for k. So it actually does give me all 3 pieces of information that I need. It says that my principal is equal to $5,000 here. So that's one part. It also says that the interest on that principal is $43.75, so this is my interest value. And then it does give me a time. It tells me that it's 1/4, 3 months. In other words, it's a quarter of a year. So those are the numbers I'm going to plug into my formula, just like so. So what we're going to do first to solve for k is take 1/4 of 5,000, and I get 1,250. And now to solve for k, I'm going to divide both sides by that value, which gives me that k is equal to 0.035. So my ending equation is going to be r equals 0.035 times p times t. So what is that 0.035 actually telling us in terms of this interest? And this actually represents the interest rate. So this right here is your rate. In terms of a percentage, we move the decimal place over 2 spots and we get 3.5%. So we know everything that there is to know about this particular problem in this simple interest. So those are your 3 different kinds of variation and a few examples to go with it, and that will conclude this tutorial.